Hi, I'm Dennis and today I'm going to present our work on tetrahedra of varying density and their applications. First, I will give a short introduction on the challenges that have to be faced when handling geometry of varying density. I will also quickly round up the necessary math for the upcoming computations, and eventually we can have a look at some cool application scenarios for the introduced methods. So let's start with the problem statement. Mesh geometry is usually given as a set of vertices connected with triangular faces. However, to simulate varying density for such objects, a common fallback solution is to use grid or octree-based voxelizations of the volume, as these small boxed volume entities are easily integratable. This, however, is only an approximation of the real volume, as the discretization introduces heavy aliasing bias. Therefore, we propose to use a more suitable volume entity, namely the tetrahedron. With the tetrahedralization of the object, we can compute accurate results based on a real input domain without introducing bias. Let the general tetrahedron be defined by its 4 vertices. Each vertex has 3 geometric dimensions x, y, and z, and is extended with a 4th dimension specifying the density. If we are now challenged with the integration of this tetrahedron, for example to compute the center of mass or the mass itself, we can use the following simplification. Under the assumption of linearly varying density, we can specify 4 base cases. For each case, we can assume one vertex with density of 1 and 3 vertices with the density being 0. Computations for these base cases are then multiplied with the density values of their corresponding vertices. Summed up, this results in simple closed-form solutions for the mass properties of a general tetrahedron. The mass, for example, is simply the tetrahedron's volume times the average density at its 4 vertices. For our first applications, we can now observe that tetrahedralized objects are nothing more than a whole lot of volume entities partitioning the input domain. Therefore, the overall mass of the object computes as the sum over all tetrahedra, and the center of mass as the mass-weighted sum over all tetrahedra. With the theorem of point masses, we can even infer the object's inertia tensor. So by now, we are at a point that if we know the geometry of our object and we know the density field, we can compute the mass properties. Now, to make things more interesting, we can also turn this problem around and say, okay, we have this geometry and we want these mass properties. How should the density field look like? Therefore, we have to first parameterize our density field. And we do this by using this sandwich formulation, where the gradient is enclosed on both sides with regions of constant minimum and maximum density. To simplify further computations, we specify the gradient to be axis-aligned and define parameters for the object's embedding in this space. Therefore, we use 2 angles for tilt and rotation and 1 parameter for the axis offset. The density field itself is specified by this function, with parameters for the gradient, its steepness, and a constant offset for minimum density. In our embedded tetrahedralized geometry, we are now facing 3 different kinds of tetrahedra. First, there are tetrahedra in regions of constant density. Their computation is trivial. Then we have tetrahedra within the gradient region. Also no problem here, we can simply use the methods introduced in the beginning. But then there are also tetrahedra which overlap regions of constant and varying density. To integrate these tetrahedra as well, we have to split them along a bisection plane. Up to symmetry or rotation, we can identify 4 possible cases to intersect a tetrahedron with a plane. As with any polyhedron, the resulting geometry again easily subdivides into tetrahedra. Now we can treat all tetrahedra with our established methods. Let's have a look on how objects behave in this embedding. Here we see a tetrahedralization of the fan disk model and the density field as parameterized with our function, visualized by this box. The density field increases from low to high within the box. Below or above the box, the field has constant minimum or maximum density respectively. the object's center of mass is shown as the red sphere, along with the principal inertial momentum axis, illustrated with arrows in cyan, magenta and yellow. With the bottom sliders we can modify the density field. Observe how the center of mass behaves as we rotate, shift or narrow the density field. As we increase the ratio from lowest to highest density value, we can push the center of mass to quite extreme positions. We can see that a suitable density field allows to modify the mass properties of the geometry and use this in the next application to balance an unstable object. Therefore, we let an optimization determine the density field parameters, where the objective function is the Euclidean distance from the embedded object's center of mass to a specified target point. Prevost et al. Proposed the Make It Stand challenge for objects, where they carved out the voxelized interior of the geometry to move the center of gravity over a stable point. They also modified the geometry, as in this case where the top sphere is shrunk and the bottom sphere is enlarged. With our approach, we do not alter the geometry, but only determine the required density field to achieve comparable results. However, this has to be seen as merely a theoretical result, as current manufacturing techniques are not yet able to print gradients of this magnitude. In this example, the gradient varies from low to high with a factor of about 20. Overall, we are not strictly limited to linear density fields. We can also use our technique to approximate other fields, as in this example, a spherical sinoidal function or a Gaussian bell curve decreasing in density with increasing distance from the surface. As the density and integration within each tetrahedron are still linear, this problem becomes a sampling issue, where each vertex samples the density field, and the resolution of the TET mesh eventually dictates the accuracy of the approximation. For a practical experiment, we chose the rocker arm object, which has a rotary mount, and due to the obvious asymmetry, the native center of mass, in red, is not on a rotation axis, and the inertial momentum is also not parallel to this rotation. To produce this object with constant density, we used a low-budget Prusa FDM printer and common slicer tools. To print varying density with this simple setup, we edited the G-code of the sliced object file and constantly modified the extrusion rate of the nozzle while printing. An example can be seen on the right, where the thickness of a single extrusion varies from top to bottom. This can also be observed on the printed rocker arm with optimized density. Both examples are photographed in front of a strong light source to highlight the varying density distribution. Now let's have a look on how this turned out. First, we see the object with constant density. And now our optimized object, which has a much smoother spinning. For our next application, we first need a little bit of background information. Here we see a Voronoi diagram in blue and a corresponding Delaunay triangulation in white. The diagram specifies cells based on the given set of input points. These are called sites and are shown in black. For each cell, we can also compute a centroid, shown in orange. A Lloyd relaxation describes the algorithm to take such a Voronoi diagram and reposition the sites to the centroids of their cells. Then recompute the diagram for the next cycle of the iteration. If we repeat this process a couple of times, the diagram converges on a centroidal Voronoi diagram, where the site positions and centroids eventually coincide. In 3 dimensions, the algorithm is basically the same, and as long as we are in Euclidean space and use the L2 norm, the integration over the convex cells is fairly easy. However, if we exchange the metric for computing the diagram, the integration becomes a bit more challenging. For example, using the L infinity norm now requires to integrate over this cell with a non-trivial and orientation-dependent distance function. Here we can again use our method for tetrahedra to approach this problem in a different way. Therefore, Each cell is split into axis-aligned fragments where the energy now linearly increases in one direction, and we can encode this in our density domain. Each fragment is then tetrahedralized, and the closed-form solutions can be summed up for each fragment and eventually for the whole cell. The three-dimensional cell is split into 6 fragments, and if we use this energy formulation to be minimized in the Lloyd relaxation, the cells eventually become more cubical, and the relaxed L-infinity diagram approximates hexahedral mesh structures. This is not limited to the space of a bounding box, but also works on restricted and clipped boundary domains. Now to summarize. The methods to compute tetrahedra of varying density are pretty simple, and existing frameworks can be easily extended. The achieved results for mass properties are precise, as the actual triangulated boundary of the input object can be used for calculations. It is fast, as we formulate the computations as matrix vector multiplications, suitable for efficient execution on GPU hardware. And we showed how versatile the approach is, with various examples from density field optimization to novel formulations of an energy term for L-infinity Lloyd relaxations. With this, I conclude my presentation and thank you very much for the attention.